The night sky holds a secret we have only just begun to suspect. For decades, we have listened for alien radio signals and heard only silence. But what if we are listening for the wrong thing entirely? What if advanced civilizations have moved beyond primitive radio waves and built something far more spectacular for their cosmic travels? Today we will uncover the theory of neutrino beacons, a hypothetical alien GPS system that could be broadcasting across the galaxy at this very moment. By the end, you will understand how ghostly particles might be the key to the greatest discovery in human history. We will explore how such a system could work and why its signals have remained hidden in plain sight. What do you believe is waiting for us in the cosmic dark? To understand this cosmic navigation system, you first need to meet its messengers. Neutrinos are among the most common particles in the universe, yet they are also the most elusive. Think of them as cosmic phantoms, ghostly wisps of matter so small they are almost without mass. They travel at velocities just a whisper below the speed of light, and their defining trait is a profound indifference to the universe they pass through. A single neutrino can fly straight through a planet like Earth, or even an entire star, as if it were not even there. For every second you stand in sunlight, trillions of these phantoms from the sun are streaming through your body, leaving not a trace of their passage. They are born in the universe's most violent and energetic events, from the steady nuclear fire of our own sun to the cataclysmic explosions of dying stars. This ghostly nature makes them incredibly difficult to detect, but it also makes them the perfect cosmic couriers. If you wanted to send a message across the vast, cluttered expanse of the galaxy, what better vessel could you possibly use than a particle that ignores every obstacle in its path? This profound silence from the stars leads us directly to one of the most haunting questions in science. Where is everybody? This is the essence of the Fermi paradox. The universe is unimaginably vast and ancient, filled with countless stars and even more planets that could support life. Statistically, the cosmos should be teeming with civilizations, their chatter filling the void. Yet when we point our radio telescopes at the sky, we are met with an eerie, unbroken silence. This contradiction is not necessarily a sign that we are alone. It could be a monumental clue that we are simply listening for the wrong thing. Think of it like this. If you were trying to contact a friend, you would not send them a message via a telegraph machine in Morse code. You would use a modern smartphone. Our search for extraterrestrial intelligence has been focused almost entirely on the cosmic equivalent of that telegraph, the radio wave. It is a technology we mastered over a century ago. A civilization thousands or millions of years more advanced than us would have long since moved on to something far more efficient and reliable. They would use a technology that does not fade over interstellar distances, one that is not drowned out by the background noise of the universe. This is not a failure of our search, but a misdirection of our focus. The great silence is not empty. It is telling us to stop listening for the familiar and start searching for the sophisticated. It points toward a communication method so advanced, so perfectly suited for galactic travel, that we have only just begun to consider its possibilities. Navigating the ocean of stars presents a problem almost beyond human comprehension. Distances are so vast that even at the speed of light, a message from one side of our galaxy to the other would take over 100,000 years to arrive. But the challenge runs even deeper than that. The galaxy is not a static painting. It is a swirling, dynamic river of stars, all orbiting the galactic center at different speeds. A star map painstakingly drawn by an ancient civilization would be utterly useless today. Its once familiar constellations stretched and distorted beyond recognition over the millennia. For any society aiming to travel between the stars, this creates a fundamental question. How do you create a map that never goes out of date? The answer might be a system far grander than any we have built, a galactic positioning system. Think of the GPS in your phone, which uses a network of satellites as fixed reference points to pinpoint your location on Earth. Now scale that concept up to an entire galaxy. An advanced civilization would need a set of fixed points that are immune to the cosmic dance of stars, beacons that remain constant over millions of years. This is where our ghostly messengers, the neutrinos, re-enter the story. A network of powerful, precisely timed neutrino emitters placed at stable locations like the galactic core or in the quiet spaces between galaxies could provide the perfect solution. Each beacon would broadcast a unique signal, a steady pulse of these phantom particles. A ship traveling through the void would only need to detect the signals from several of these beacons. By measuring the tiny differences in the arrival times of these pulses, the ship's navigation computer could perform a feat of cosmic triangulation, calculating its exact position within the galaxy with astonishing precision. It would be a map written not in starlight, but in the most fundamental fabric of space-time, a constant and reliable guide through the endless dark. So why choose a ghost for a messenger? The answer lies in the very properties that make neutrinos so elusive. They are the universe's ultimate long-distance travelers, possessing a set of perfect qualities for a galactic communication network. First, neutrinos are electrically neutral. This single fact makes them immune to the powerful magnetic fields that twist and warp the paths of other particles across space. While a radio wave or a beam of charged particles can be sent wildly off course by a passing nebula or a star's magnetic influence, a neutrino travels in a perfectly straight line. Its path from point A to point B is a direct, unwavering thread through the cosmos. It ignores every interstellar dust cloud and every swirling magnetic storm. This guarantees that any message it carries arrives exactly as it was sent, its trajectory a flawless indicator of its point of origin. Second, these particles move at velocities incredibly close to the speed of light itself. A signal sent via neutrino is not just direct, it is nearly instantaneous on a galactic scale. There is no faster way to send information across such mind-bending distances. And third, we have their incredible penetrating power. A radio wave, the kind we have been searching for, is fragile. It can be scattered by interstellar gas, absorbed by thick cosmic dust, or simply drowned out by the cacophony of background radiation that fills the universe. It is like trying to hear a whisper across a crowded, noisy stadium. A neutrino, however, experiences none of this. It passes through planets, stars, and entire galaxies as if they were made of empty air. A neutrino beacon signal would never fade, never distort, and never be lost. It would shine through the most chaotic regions of the galaxy with perfect clarity, a constant and unwavering lighthouse in the void. The sheer scale of engineering required for such a beacon is almost beyond imagination. To generate a focused beam of neutrinos powerful enough to be detected across the galaxy, a civilization would need to command energy sources that dwarf our entire planetary output. We are not talking about building a larger version of our particle accelerators. We are talking about harnessing the fundamental engines of the cosmos. One possibility is that they would tap into the power of a star, constructing a Dyson sphere not just to collect energy, but to convert it. Picture a vast, intricate structure completely enveloping a neutron star. This stellar corpse, spinning rapidly and possessing a gravitational field trillions of times stronger than Earth's, could act as a natural particle accelerator of unimaginable power. The civilization would use this immense force to catalyze reactions that spawn trillions upon trillions of neutrinos, then focus them into a tight, coherent beam. But generating the particles is only half the challenge. The real marvel is in the modulation. How do you etch a message, a complex navigation signal, onto these phantom particles? It would require technology to precisely control the timing, energy, and perhaps even the quantum states of the neutrinos as they are emitted. This would be like trying to carve an intricate message onto individual photons in a laser beam, but infinitely more difficult. The machinery to achieve this would need to operate on a scale we can barely conceive, possibly using gravitational lensing or quantum fields we have not yet discovered to shape the beam. This is not merely a powerful transmitter, it is a device that writes information onto the fabric of reality itself, creating a signal that echoes for millions of years without ever fading. But with such a powerful signal echoing through the cosmos, how could we possibly know it was made by intelligence and not just a cosmic accident? This is the ultimate puzzle for the astronomers who listen for these ghosts. The universe is already filled with natural sources of neutrinos, a constant background hiss from the sun, from supernovae, and from distant, active galaxies. To find an artificial signal, you are not listening for a louder noise. You are searching for a whisper of order within the chaos. The first and most telling clue would be a pattern that defies natural explanation. Natural neutrino emissions are messy and stochastic. They arrive in a random, unpredictable cascade. An artificial beacon, however, would likely carry a signature of intent. Scientists would search for a signal with an unnaturally perfect timing, a series of pulses separated by precise mathematical intervals. Think of it like hearing a steady, rhythmic drumbeat in the middle of a thunderstorm. The storm is powerful but random. The drumbeat is a message. Another signature would be modulation, a way of encoding complex information onto the beam itself. This could be a deliberate, repeating sequence that changes in a way no known physics could produce, perhaps shifting the energy levels of the neutrinos in a pattern that spells out a sequence of prime numbers or some other universal constant. It would be a fingerprint of design, a structure so complex and orderly that its origin could only be a mind. This is where our most sensitive instruments on Earth become vital. Deep within the ice of the South Pole, the Ice Cube Observatory watches for the faint flashes of light created when a rare neutrino interacts with the ancient ice. In Japan, the Super Kamioke detector, a colossal tank of ultra-pure water surrounded by sensitive light sensors, performs a similar watch. These are not simple listening devices. They are cosmic forensic labs. Their computers sift through millions of events every day, searching for that one in a billion pattern, that single thread of intelligent design woven into the background tapestry of the universe. They are not just waiting for a signal, they are hunting for a ghost with a purpose. So what kind of message would be worthy of such a monumental effort? The most straightforward answer is a simple cosmic address. Each pulse from a beacon could be a constant identifier, a unique signature saying, "I am beacon Alpha, located at these specific galactic coordinates." A ship receiving signals from 3 or 4 such sources could triangulate its position with perfect accuracy. It would be the ultimate "you are here" dot on an unimaginably vast map. Yet this purely functional data seems almost too simple. A civilization capable of building stellar engines would likely embed far richer information into their signal. Think of the data your car's navigation system receives beyond just location. It gets traffic updates, road closures, and weather alerts. A galactic beacon could serve a similar purpose. Its modulated signal might contain a full ephemeris, a dynamic model of the galaxy's moving parts. It could broadcast the predicted paths of stars, the locations of newly formed nebulae, or even real-time alerts about dangerous cosmic events. A nearby gamma-ray burst, for instance, would be a lethal wave of radiation sweeping across entire star systems. A beacon could provide an early warning, a critical safety broadcast for any vessel traveling the interstellar lanes. This transforms the network from a simple map into a living, breathing galactic information highway. But the most tantalizing possibility is that the navigation data is merely the opening line of a conversation. The beacon's pulse could be a handshake, a standardized protocol designed not for machines but for minds. The precise timing of the pulses might encode a primer, a set of universal mathematical and physical constants that any technologically advanced species would recognize. This would be the first step in a complex dialogue, a way of saying we are here and we know you are listening. Once that basic language is established, the beacon could begin transmitting more, perhaps even instructions on how to build a receiver for the next, more complex layer of communication. The navigation signal would then be just the envelope, and inside could be a library waiting to be opened. This brings us to one of astronomy's greatest unsolved mysteries, a single event that has taunted researchers for decades. In August of 1977, a radio telescope at Ohio State University recorded a signal so powerful and so unusual that the astronomer who saw the printout simply circled it and wrote, "Wow." It was a strong, narrowband radio burst, exactly the kind of signal we would expect from an extraterrestrial intelligence. And then, just as suddenly as it appeared, it vanished. It was never heard again. For over 40 years, the WOW signal has stood as a ghost in the machine, a perfect candidate for an alien message with no way to prove it. But what if we have been misinterpreting its origin entirely? What if it was not the message itself, but merely an echo of something far greater? Consider the theory of a neutrino beacon. To generate such a focused beam of phantom particles, a civilization would be manipulating energies on a stellar scale. This process, this immense focusing of power, might not be perfectly clean. It could produce unintended side effects. Just as a powerful electrical transformer hums with an audible buzz, the machinery of a neutrino transmitter might leak a secondary signal into the electromagnetic spectrum. This would not be a carefully crafted radio message. It would be a burst of static, a powerful but simple screech caused by the sheer force of the emission process. The WOW signal fits this profile perfectly. It was incredibly strong, very narrow in frequency, and lasted for 72 seconds, the exact duration the telescope's fixed antenna would have taken to scan across a single point in the sky. It was a fleeting, brilliant flash, as if a cosmic spotlight had briefly switched on and then off. Perhaps we were not listening to a deliberate radio broadcast. Perhaps we were hearing the faint, accidental radio frequency hum of a galactic lighthouse, a machine so vast its mere operation briefly outshone the stars. This single, unexplained event could be our first indirect evidence of a technology operating on a scale we can barely comprehend. A technology that uses the silent, ghostly world of neutrinos to speak across the light years. The WOW signal might have been a whisper, but some cosmic events are deafening roars. Our own galaxy is a bustling metropolis of stars, but the true scale of the universe lies in the vast, empty voids between galaxies. For a civilization with truly interstellar ambitions, a local GPS within the Milky Way would be only the first step. The next logical phase would be an intergalactic navigation network, a system of beacons designed to guide travelers across the unimaginable chasms that separate island universes. This concept stretches the neutrino beacon theory to its absolute limits, demanding energy sources and engineering that border on the divine. The distances involved are not just larger, they are of a different order of magnitude entirely. A journey to our nearest galactic neighbor, Andromeda, would take a beam of light 2.5 million years. To send a detectable signal across such a gulf, a beacon would need to be powered by something far beyond a single star. The only conceivable anchors for such a system would be the most stable and energetic objects in the known universe, the supermassive black holes that lurk at the heart of every galaxy. Imagine a civilization capable of building a structure in the violent space surrounding a black hole's event horizon, using its immense gravitational and rotational energy to power a transmitter of godlike power. The neutrino beam it produced would be a needle-thin spear of information, fired with such precision that it could still be decoded millions of light years away. This is no longer just engineering, it is cosmic architecture on a scale that redefines what is possible. And if such incomprehensible machines are indeed out there, their operation might not be perfectly silent. The sheer energy required to punch a signal across intergalactic space could produce spectacular side effects. This leads us directly to one of the most persistent and puzzling mysteries in modern astronomy: fast radio bursts. These are incredibly brief, intensely powerful flashes of radio waves that come from deep space, often from billions of light years away. They last for only milliseconds, yet in that fleeting instant, they can release more energy than our Sun does in 80 years. Their origins remain a complete enigma. But what if we are not seeing a natural cataclysm? What if a fast radio burst is the cosmic static, the accidental radio screech, from an intergalactic neutrino beacon powering up for a transmission? The process of focusing a neutrino beam across such distances could unleash a torrent of secondary electromagnetic radiation, a brief, brilliant flash that leaks into the radio spectrum. We would be witnessing not the message itself, but the shadow of the machine that sends it, a faint echo of a technology so advanced its mere operation mimics the most violent explosions in the cosmos. It is a humbling thought that our greatest astronomical mysteries might not be the death cries of stars, but the operational background noise of a galaxy-spanning civilization going about its business. This chilling possibility forces us to confront a deeper cosmic question. Why would a civilization go to such incredible lengths to build a galaxy-spanning network, only to encode its signals in ghost particles? The answer might lie in one of the most unsettling solutions to the Fermi paradox, the dark forest hypothesis. This theory imagines the universe as a vast, dark woodland where every civilization is a hidden hunter, terrified of revealing its location. In a forest teeming with unknown life, any sound or signal could attract a predator far more advanced and hostile. The safest strategy for survival is absolute silence, to stay hidden and make no sound at all. If this is the true nature of our cosmos, then the great silence is not a sign of emptiness, but of universal and rational fear. So why would any species risk building a system of bright, powerful beacons? The key is that a Neutrino GPS does not have to be a shout into the darkness. It could be a whisper deliberately designed to be invisible to all but the most advanced listeners. Think of it like a high-frequency dog whistle. The sound is being broadcast openly, but only a creature with the specific ability to hear that particular pitch can even perceive it. A neutrino beacon network could function in exactly the same way. Its signals are not hidden. They are flooding the galaxy right now. But to a species that has not yet mastered particle physics and built colossal underground detectors, the signal is entirely undetectable. It passes through their world without a trace, completely unnoticed. This creates a perfect cosmic filter. Only a civilization that has reached a certain technological and peaceful maturity, one capable of harnessing immense energy and understanding the subtleties of quantum physics, would possess the tools to notice the beacon and decipher its code. It is a system that, by its very design, avoids contact with primitive species who might see the beacon as a target or a threat. It is not a message of greeting. It is a piece of essential infrastructure, a tool left out in the open for those who are ready and wise enough to use it. The network ensures that only those who have learned to listen to the universe's quietest whispers are given the keys to the galaxy. The history of our search for these cosmic ghosts is already filled with strange whispers we could not explain. When a star exploded in a nearby galaxy in 1987, our primitive neutrino detectors recorded a fleeting burst. For 19 seconds, a handful of these phantoms arrived from the dying star, an event that perfectly matched our models of a supernova. It was a triumph of astronomy, the first time we had ever observed neutrinos from beyond our solar system. But what if that natural cosmic explosion provided the perfect camouflage for an artificial signal? A sophisticated beacon would not necessarily broadcast constantly. To conserve immense power or to avoid drawing attention, it might pulse only at specific intervals, or it might hitch a ride on nature's own fireworks. A supernova's chaotic blast of neutrinos would be the ideal hiding place. An artificial pulse, perfectly timed to coincide with the explosion, could be hidden within the natural data. Scientists would see the expected surge from the dying star and dismiss the entire event as purely natural. But buried within that 19-second window, there might have been a series of pulses too orderly, too precisely spaced to be born from chaos. It would be like hearing a perfectly rhythmic melody played on a piano during an earthquake. You are so focused on the tremor that you miss the music. Our detectors have been collecting data for decades, and within those vast digital archives may lie patterns we have simply overlooked. The very first dedicated neutrino observatory, the Homestake experiment, was built deep within a South Dakota gold mine to be shielded from cosmic rays. It famously detected neutrinos from the sun, but its data also contained unexplained fluctuations, minor anomalies that were attributed to background noise or equipment error. We now understand that the universe is filled with a constant, low-energy neutrino background, a relic from the Big Bang. This cosmic hiss is the ultimate static. But what if a very faint, very slow artificial signal is hidden within that static? A beacon designed for truly long-term navigation might broadcast a single identifying pulse not every second, but once every year or even once every century. Its signal would be so slow and so faint that our current analysis methods, which are designed to find sudden bursts, would automatically filter it out as irrelevant noise. We are like someone listening for a shout in a crowded room, while a patient messenger in the corner is tapping out a complex code with unimaginable patience. The search for these subtle patterns is the new frontier. Modern experiments like IceCube and SuperCamioc and generate terabytes of data every single day. Within that ocean of information, the telltale signature of a beacon would not be a loud, obvious siren. It would be a subtle correlation, a statistical ghost. Imagine looking at a vast field of tall grass blowing in the wind. The motion appears completely random, but if you had a high enough vantage point and watched for long enough, you might notice that one small patch of grass sways in a faint, repeating pattern every time the wind blows from the east. This is what astronomers are now doing with neutrino data. They are developing algorithms to search for weak periodic signals, for strange coincidences where neutrinos from a specific patch of sky arrive with a consistent energy or a rhythmic timing that defies any known celestial process. They are no longer just waiting for a message. They are sifting through the sands of time itself, looking for the footprints of a builder who passed by millions of years ago. The greatest discovery in human history may not be a signal we receive in the future, but a pattern we finally recognize from the past, a message that has been arriving all along, waiting silently in the data for us to learn how to see. The staggering energy demands for such a beacon are the true barrier between our civilization and a galactic one. To make a neutrino beam detectable across just 1,000 light-years, the power required is almost beyond human comprehension. Let us put this into perspective using our own sun. Our star, a continuous nuclear furnace, floods the entire solar system with light and heat. Yet the energy it emits as neutrinos, while immense, is spread out in all directions, a gentle cosmic rain. To create a focused beam powerful enough to stand out against the universe's natural neutrino background at such distances, you would need to concentrate the entire energy output of the sun not for a second, but for years into a single, narrow needle of particles. This is not just a large number, it is a statement about the scale of cosmic engineering. So what power source could possibly achieve this? The first candidate is one of pure, unadulterated conversion, matter-antimatter annihilation. When a particle of matter meets its antimatter counterpart, they obliterate each other, converting 100% of their mass into pure energy. It is the most efficient reaction known to physics. To power our galactic lighthouse for even a single day, a civilization would need to annihilate a mass of fuel equivalent to a large mountain. The engineering required to produce and safely contain such vast quantities of antimatter is a technology that belongs to the gods of physics. A second, even more mind-bending possibility involves not creating energy but stealing it from the universe itself. This is the Penrose process, a theoretical method to extract energy from a spinning black hole. Imagine constructing a vast structure, a ring of unimaginable strength, around the black hole's event horizon. If you could fire a mass into a specific region of space just outside the event horizon, known as the ergosphere, the black hole's immense rotational drag would rip the object apart. One fragment would be swallowed, but the other could be flung back out with more energy than it entered with. You would have literally taken energy from the black hole's spin. A civilization could use this trick to power their beacons for eons, slowly breaking the spin of a cosmic monster to light their way through the galaxy. The most speculative idea of all involves controlled micro-singularities, tiny black holes no larger than an atom. According to theory, such an object would radiate Hawking radiation, releasing a tremendous amount of power until it eventually evaporates. Harnessing even one would be like holding a miniature, dying sun in a magnetic bottle, a contained stellar explosion providing the ultimate battery. These are not just power plants, they are acts of cosmic architecture, forcing us to ask what kind of mind could build with the very fabric of space-time as its material. A single cosmic lighthouse would be a lonely and useless landmark. For a true galactic positioning system to function, you need a constellation. Picture not one, but dozens, perhaps hundreds of these immense beacons scattered across the galaxy, each one a fixed point of reference in the swirling stellar chaos. Their placement would be a work of supreme strategic genius, designed for maximum stability and coverage. The most logical anchor points would be locations that are themselves stable over millions of years. The supermassive black hole at the very center of our galaxy, for instance, is a natural candidate. Its immense gravity makes it the most fixed object for tens of thousands of light years around. Other beacons might be positioned at the gravitational sweet spots within star systems, the so-called Lagrange points, where the pull of a star and its planets balance out to create a zone of perfect orbital stability. Some could even be adrift in the deep, dark quiet of interstellar space, far from the light and interference of any star, acting as silent sentinels in the void. The true magic, however, lies not just in their placement, but in their perfect synchronization. Each beacon would emit its unique identifying pulse, but these pulses would be timed against a universal clock. This clock would likely be based on a fundamental, unchanging constant of physics, something any advanced civilization would understand, like the spin of a pulsar or the decay rate of a subatomic particle. Imagine each beacon is a drummer in a vast galactic orchestra, each beating its drum in a perfectly synchronized rhythm. A starship traveling through the spiral arms would listen for these drums. It would hear the pulse from beacon Alpha, then a moment later, the pulse from beacon Beta, and then from Gamma. The tiny differences in the arrival times of these pulses are the key. Just as your brain uses the slight delay between a sound reaching your left and right ear to locate its source, the ship's computer would use these time delays to perform an act of cosmic triangulation. By measuring the precise intervals, it could calculate its exact position relative to each beacon, plotting a perfect "you are here" dot on a map of the entire Milky Way. This network would transform the galaxy from an unnavigable wilderness into a charted territory, its hidden pathways illuminated by the silent, rhythmic ticking of ghostly clocks. But this grand vision of a galactic internet, a network of synchronized lighthouses, runs headfirst into a seemingly insurmountable physical barrier. How do you focus a particle that refuses to interact with anything? We can build a laser to create a perfectly straight beam of light and a radio dish to focus radio waves, but a neutrino is a ghost. It passes through any lens or mirror we could ever construct as if it were not there. Directing these phantoms into a tight, coherent beam is the ultimate engineering puzzle, and its potential solutions stretch our understanding of physics to the absolute limit. One speculative idea involves not fighting their ghostly nature, but using the universe's own gravity to our advantage. The gravitational fields around massive objects like neutron stars are so intense that they warp the very fabric of space-time, bending the paths of everything that passes by, including light. This is called gravitational lensing. An advanced civilization could position their neutrino emitter at a precise point relative to a neutron star. As the neutrinos stream out in all directions, the star's immense gravity would act as a natural cosmic lens, bending and focusing a large fraction of them into a narrow, amplified beam shooting off into the galaxy. It would be like using a mountain to focus the wind, a feat of astronomical scale engineering. Another possibility is to create the neutrino equivalent of a laser. A laser works by stimulating the emission of light waves that are all in perfect sync or coherent. What if you could do the same for neutrinos? The concept of a neutrino laser or nucleator is purely theoretical, but it suggests a technology that could cause neutrinos to be emitted in a coherent stream, a perfectly orderly march of particles that would naturally stay tightly bundled over immense distances. This would require a level of control over quantum processes that we can only dream of, perhaps using exotic states of matter or energy fields we have not yet discovered. A third, even more exotic solution might involve creating temporary guide rails for the neutrinos. While neutrinos do not interact with electromagnetic fields, some theories suggest they might be influenced by certain types of exotic matter fields or through subtle quantum effects. Imagine generating a transient corridor in space, a tunnel defined by a specific energy state that gently shepherds the neutrinos along a predetermined path, preventing them from spreading out. It would be like creating an invisible fiber optic cable stretched across light years, a highway for information built from the fundamental forces of nature. These are not just bigger versions of our technology, they are technologies that rewrite the rules, turning the universe's most elusive particle into a precisely aimed cosmic arrow. The universe itself could provide the perfect timekeeper for this ghostly network. Our own GPS satellites rely on atomic clocks of astonishing precision, but for a system spanning the galaxy, you would need a clock that never drifts, a rhythm that echoes across millions of years. The steady, metronomic spin of a millisecond pulsar offers one such solution. These cosmic lighthouses are the rapidly rotating cores of dead stars, beaming out radiation with a regularity that rivals our best timekeeping devices. A civilization could designate one specific, exceptionally stable pulsar as the galaxy's master clock. Every beacon in the network would synchronize its unique pulse to this celestial metronome, each one ticking in perfect universal time. A starship navigating the void would not just listen for the beacons, it would compare their arrival times against its own internal copy of this universal clock. The principle is one of simple yet profound geometry. Imagine you are standing in a vast, dark field, and you hear three drummers, each a different distance away, all beating in perfect sync. You hear the beat from the closest drummer first, then the next, and finally the one farthest away. The precise delays between when the drum should have sounded according to the master clock and when you actually hear it are your data points. Each delay is a measure of the distance you are from that specific drummer. With signals from 3 or more synchronized beacons, your ship's computer can triangulate its exact location in 3-dimensional space with pinpoint accuracy. But this perfect synchronization holds within it a potential secret, a way to peer back into the deep past. Even a pulsar's spin slows down over eons, an imperceptible drift across millennia. If the master clock itself has a known, minuscule decay rate, then any tiny, accumulated error in the timing of the beacon signals would not be a flaw. It would be a timestamp. By measuring the infinitesimal lag in the rhythm, a receiving ship could calculate not just where it is, but when the beacon network was established. The signal would carry its own age, revealing that you are listening to a map crafted 1,000,000 years ago, a timeless guide left behind by architects who may have long since vanished. But who was this vast and silent network truly built for? The answer to that question carries profound implications. One possibility is that the Neutrino Beacons are simply a piece of public works, a cosmic highway system maintained by the civilization that built it for its own use. In this scenario, the galaxy is not empty but bustling with traffic we are simply unable to see. Their ships move along predetermined routes, their navigation computers constantly listening to the steady, rhythmic pulses from the beacons, much like our cars follow GPS signals today. The network would be essential infrastructure, as vital to their interstellar economy as roads and bridges are to ours. It would be a tool, not a message, and its builders might be entirely indifferent to whether any other species ever stumbles upon it. Yet there is another, far more compelling possibility. What if the network is not just for them? What if it is a test, the ultimate entrance exam for the galactic community? A civilization capable of such engineering would understand that life evolves slowly and that intelligence must crawl its way up the technological ladder. They would know that any species that learns to detect neutrinos, to build colossal observatories deep underground, has reached a specific level of maturity. It has mastered fundamental physics and has likely achieved a degree of global cooperation to fund and build such projects. By encoding their navigation data in these ghostly particles, they create a perfect filter. They are not broadcasting a loud, obvious hello that might frighten a primitive world. Instead, they have left a set of keys hanging on a hook in plain sight, but the hook is placed so high that only a species that has grown tall enough can possibly reach it. The very act of detecting the signal proves you are ready for the next step. This transforms the beacon from a mere tool into a message in a bottle of cosmic proportions, a deliberate challenge thrown down to the stars. It asks a silent question of every emerging intelligence in the galaxy. Are you wise enough to listen to the universe's quietest whispers? Have you grown tall enough to reach the keys? Buried deep within the pristine ice of the South Pole, a colossal digital eye stares into the heart of the Earth itself. This is the Ice Cube Neutrino Observatory, a telescope built not from glass and metal, but from a cubic kilometer of ancient transparent ice. Strung throughout this frozen expanse are over 5,000 sensitive light sensors, waiting in total darkness. They are not looking for light from the stars above, but for the faint, telltale blue flashes created on the rare occasion that a cosmic neutrino, after traveling for millions of years, finally collides with an atom in the ice. Each of these tiny flashes is a victory, a ghost finally caught. But Ice Cube is just one hunter in a growing global network. Soon, its counterpart will rise from the depths of the Mediterranean Sea. The KM3 NET telescope will transform a vast volume of deep ocean water into a similar neutrino trap. Its thousands of detectors looking through the Earth toward the galactic center, a prime location to spot any potential beacon. These instruments represent the cutting edge of our search, our first real attempt to listen to the universe's quietest channel. Their method is one of brute force statistics and immense patience. They do not listen for a single sound, but for a pattern emerging from an ocean of noise. Every second, countless neutrinos from the sun and other natural sources pass through their volumes, creating a constant, random background. An artificial signal would not be a single loud bang. It would be a subtle statistical anomaly, a persistent whisper from one specific direction in the sky that defies the random chaos. It is the ultimate search for a needle in a cosmic haystack, where the haystack is the entire universe and the needle is a particle that thinks solid matter is a suggestion. The challenge is not just detecting neutrinos, but discerning a faint, ordered rhythm within a deafening, chaotic symphony. Our current detectors are only just becoming sensitive enough to perform this incredible forensic task. They are learning to sift through the sand of the cosmos, grain by grain, looking for the one grain that is not sand at all, but a perfectly crafted piece of glass. The discovery would not announce itself with a blaring siren, but as a quiet, persistent correlation in the data that simply refuses to go away, a pattern that insists it was made by a mind. This history of astronomy is filled with moments where nature perfectly mimics the signature of intelligence. The discovery of pulsars in 1967 is the most famous example. Astronomers detected a radio signal from deep space that pulsed with a rhythm more perfect than any known natural object. It was so unnervingly regular that the research team half-jokingly labeled it LGM-1 for little green men. They had genuinely considered the possibility that they were listening to a beacon. Of course, they soon realized the true source was a spinning neutron star, a cosmic lighthouse sweeping its beam across the galaxy with the precision of a celestial clock. These pulsars are, in a very real sense, natural neutrino beacons, as their intense magnetic fields and rapid rotation also produce powerful streams of these ghost particles. So if nature already provides these perfect, rhythmic signals, why would any civilization go to the monumental effort of building their own? The answer may lie in a simple but profound distinction. A natural pulsar is a clock, but it is not a clock you can set. Its rhythm is fixed by the physics of its birth and spin. It cannot change. It cannot carry complex information. It can tell you the time, but it cannot tell you where you are unless you already have a detailed, pre-existing map of every pulsar in the galaxy. An artificial beacon, by contrast, would be programmable. Its pulse could be modulated to encode a galactic ephemeris, safety warnings, or even a primer for communication. It would be a dynamic, living map, not a static landmark. But this very distinction opens up a staggering possibility. What if a civilization did not build a beacon from scratch, but instead engineered one? The universe has already done the hard work of creating the power source, the very definition of stellar-scale engineering. A spinning neutron star is a flywheel of unimaginable energy. An advanced species might find it far more efficient to hijack this natural engine. They could construct a structure, a Dyson sphere-like ring, or a network of energy collectors around the pulsar. This megastructure would not just harvest the star's radiant energy, it would interact with its powerful magnetic fields. By carefully manipulating these fields, they could impose a subtle modulation onto the pulsar's natural neutrino and radio emissions. The underlying pulse would remain, preserving its appearance as a natural object to any casual observer. But layered on top of that steady beat would be a second, more complex signal, a whisper of code embedded within the roar. To anyone who did not know what to look for, it would just be another pulsar. But to a species that had learned to decipher the modulation, it would be a disguised lighthouse, its signal containing a wealth of navigational data. This would be the ultimate cosmic camouflage, using nature's own brilliance to hide a message in plain sight. The galaxy could be filled with these engineered pulsars, and we would have no way of knowing because we assume their perfect, natural rhythm is the only thing they have to say. The moment our computers flag that persistent, rhythmic pattern in the data, human history splits into a before and an after. The discovery of an artificial neutrino beacon would not be a slow dawning realization, but an instantaneous paradigm-shattering event. In a single stroke, the ancient question of whether we are alone in the universe would be answered with a definitive and breathtaking no. We would know with absolute certainty that we are not the only children of the cosmos to have looked up at the stars and dreamed of what lies beyond. This knowledge alone would fundamentally rewire our perception of our own place in the grand scheme of things, transforming the universe from a beautiful but empty museum into a shared, living neighborhood. The philosophical and cultural shockwaves would ripple through every society on Earth, challenging belief systems, inspiring new art and science, and uniting humanity with a common cosmic identity. But the beacon's gift would be far more than just an answer. It would be a key. The very existence of such a structure proves that physics as we understand it is not the final word. It demonstrates that energies can be harnessed and particles can be controlled on a scale we currently deem impossible. The beacon is a testament to engineering principles we have not yet discovered, a working model of technologies that transcend our wildest theories. Deciphering its signal would be like being given the complete blueprint for a starship when we have only just learned to build a bicycle. It would hand our scientists and engineers a 1,000-year head start, providing a concrete goal and a living textbook written in the language of neutrinos. And then there is the map itself. Imagine possessing a complete dynamic chart of the Milky Way, constantly updated with the safest and most efficient routes between the stars. This would not be a theoretical exercise. It would be a practical, turn-by-turn navigation system for our first interstellar voyages. Our generation's ambition might shift from planting a flag on Mars to following the beacon's coordinates to a specific, promising star system, a destination chosen not at random, but with the guidance of an intelligence that has already charted the way. The beacon would catapult us out of our cosmic cradle, not as blind explorers, but as travelers with a confirmed destination and a verified path to get there. We would step into a new era, not as orphans of the cosmos, but as heirs to a galaxy that has been waiting for us to learn how to listen. Yet this incredible gift might also be the universe's most dangerous test. Building a beacon is an act that reveals a civilization's location and technological prowess, a cosmic shout that echoes for millions of years. What if that shout attracts the wrong kind of attention? Science fiction has long played with this terrifying idea, the concept of a predatory species lurking in the dark, listening for any sign of new intelligence to conquer or consume. In this grim scenario, a navigation network would be the ultimate trap. It signals not a guide but a dinner bell. The very act of detecting and using the beacon could lead a hostile force directly to our solar system. But the more realistic danger may not be an alien invasion fleet, but the knowledge itself. Deciphering the beacon's code would be like being handed the keys to a starship's engine without an instruction manual. We would be unlocking physics and energy sources far beyond our current understanding, technologies we have not yet matured enough to handle responsibly. Think of humanity's history with nuclear fission. We discovered a fundamental force of nature, and our first instinct was to turn it into a weapon of unimaginable destruction. Now project that forward. What if the beacon's signal contains the principles for manipulating gravity, for creating controlled singularities, or for initiating matter-antimatter reactions on a planetary scale? In the wrong hands, or even in well-meaning but unprepared hands, that knowledge could be catastrophically destabilizing. It could hand a single nation or group the power to dominate the entire planet, or worse, accidentally trigger an event that could sterilize a world. The beacon would not just be a map, it would be a test of our global character, forcing us to prove we can handle the fire of the gods without burning down our own house. This silence might not be a sign of our failure, but a reflection of our youth. We are the new arrivals in a cosmos of unimaginable age. The galaxy has been forming stars and potentially nurturing civilizations for billions of years before our solar system even began to coalesce from cosmic dust. If a network of neutrino beacons was constructed in that deep past, its architects may have long since vanished, transcended into another form of existence, or simply moved on. The beacons themselves, while built to last for eons, might be operating on a timescale we can barely comprehend. Their signals could be fading, like a lighthouse whose bulb has dimmed after 1,000,000 years of continuous use, now emitting a pulse so faint that it slips below our current detection threshold. Or consider a more profound possibility. This technology might be so universal, so fundamental to a mature galactic culture, that it has become the background static of civilization. To them, it is not a spectacular discovery, it is simply infrastructure. It would be like asking a medieval peasant why he cannot see the global internet. The signals are all around him, but he lacks the very concept of a computer or a router to perceive them. The neutrino network could be so seamlessly integrated into the workings of the galaxy that it has become invisible, a utility as commonplace and unnoticed as the cosmic microwave background radiation, the leftover heat from the Big Bang. We are listening for a shout in a crowded room, but the conversation has long since evolved into a subtler, more efficient language we have not yet learned to hear. Our search is not in vain, it is simply premature. We are like the first biped standing on the shore of a vast ocean, only just beginning to wonder if the faint, rhythmic sound we hear is the tide, completely unaware that entire civilizations are sailing just beyond the horizon. The hunt for the ghost signal has moved from the ice of the South Pole to the silicon brains of supercomputers. Our most powerful detectors have been collecting a flood of data for years, a digital ocean so vast that no human team could possibly drink from it. The challenge is no longer one of raw detection, but of sophisticated pattern recognition. We are searching for a whisper of order in a hurricane of cosmic noise, and our newest ally in this search is artificial intelligence. These machine learning algorithms are not programmed with a single, specific signal in mind. Instead, they are trained on a diet of pure chaos. Scientists feed them countless streams of simulated natural neutrino data, the expected hiss from the sun, the random bursts from supernovae, and the steady drizzle from atmospheric cosmic ray collisions. The AI learns the signature of a universe governed by chance and physics. It internalizes the rhythm of randomness. Then, it is set loose on the real data collected by observatories like IceCube. Its sole purpose is to find the anomaly, the pattern that breaks the rules. It looks for correlations that a human eye would dismiss as a statistical fluke. A faint but persistent pulse from a single patch of sky, repeating at intervals that are mathematically too perfect. A subtle synchronization between neutrinos arriving from different directions, as if they were all stamped with the same cosmic timecode. The AI sifts through trillions of data points with inhuman patience, searching for the ghost that marches to the beat of a different drum. It is the ultimate detective, trained to spot a single deliberate footprint on a beach churned by countless natural waves. This technological leap is what makes the current search fundamentally different from all that came before. We are no longer just listening. We are teaching machines to understand the silence so they can recognize the first note of a song. Our current detectors are like the first crude ears straining to hear a symphony through a thick wall. The next generation of instruments will tear that wall down. These are not mere upgrades, they are leaps into a new realm of perception, colossal mega-projects designed to catch the universe's quietest sounds. One such endeavor is the Pacific Ocean Neutrino Experiment, known as P1. Its vision is as breathtaking as its scale. Instead of using a cubic kilometer of ice, it will transform a vast volume of the deep, dark Pacific Ocean into a neutrino trap. Imagine a network of floating platforms off the coast of Canada, each lowering strands of light-sensitive detectors several kilometers down into the abyssal plain. This aquatic observatory will use the ocean's natural clarity as its medium, creating a digital ear the size of a mountain range, listening for the faint blue flashes of ghostly interactions. Its sheer volume will allow it to capture far more neutrinos than any existing detector, increasing its chances of spotting a faint, repeating pattern hidden in the data. But P1 is not alone. On land, deep within a former gold mine in South Dakota, a different kind of giant is taking shape. The Deep Underground Neutrino Experiment, or DUNE, will fill immense caverns with liquid argon, a medium so pure that it can record a neutrino's passage in exquisitely detailed three-dimensional tracks. It will be like swapping a blurry photograph for a high-definition movie, allowing scientists to not only detect a neutrino but to study its energy and type with unprecedented precision. This clarity is vital for distinguishing an artificial signal from a natural one. A beacon's pulse might not just be a timing code, it could be a specific mix of neutrino flavors or a distinct energy signature that nature rarely, if ever, produces. These colossal instruments and others like them planned around the world represent a fundamental shift in our search. Their increased sensitivity is not just about hearing more noise. It is about developing the auditory resolution to pick out a single, perfectly tuned note from a cosmic cacophony. They are our best and perhaps last great hope for catching the faint, rhythmic whisper of a galactic map, a signal that has been patiently waiting in the dark for a listener to finally grow sophisticated enough to understand its language. The journey from a ghostly particle to a galactic map is a story written in the universe's quietest language. We began with a phantom, a neutrino so elusive it passes through worlds untouched, and followed its trail to one of the most breathtaking possibilities in modern science. The theory of neutrino beacons emerges not as wild speculation, but as a compelling and logical answer to a series of profound cosmic puzzles. It explains the great silence not as emptiness, but as a shift in technology, a move from the noisy radio waves we understand to a sophisticated, silent network we are only just learning to detect. It provides an elegant solution to the monumental challenge of navigating a galaxy in motion, offering a dynamic, real-time positioning system built to last for eons. And it transforms our greatest astronomical mysteries, from the wow signal to fast radio bursts, from cosmic accidents into potential side effects of a technology operating on a scale we can barely fathom. This is not a simple idea. It demands a mastery of physics and engineering that borders on the mythical, from harnessing black holes for power to bending gravity itself to focus a beam. Yet for all its grandeur, the concept fits perfectly. It uses the universe's most reliable courier, a particle that ignores all obstacles, to deliver a message that never fades. It acts as a perfect filter, ensuring that only a mature, peaceful species, one capable of global cooperation and profound scientific insight, would ever be able to find the keys to the galaxy. The evidence is not yet in our hands, but the possibility is now forever in our minds. So the next time you find yourself under a clear night sky, look up at the vast expanse of stars. Do not just see the pinpricks of light, see the potential highways between them. Think of the silent, rhythmic pulses that might be flooding through that space, through our planet, and through us at this very moment, carrying a map to wonders beyond our current imagination. The greatest discoveries are not behind us. They are hanging in the dark, waiting for us to be clever enough and patient enough to finally see the